So we've learned a few weird things about subatomic particles, including the wave-particle duality. And now we're going to learn even weirder things about time and the special theory of relativity. Before we can jump into that, we need to discuss Einstein's postulates. So a postulate is essentially a theory itself, but more so it's a fact that is assumed true in order to develop a theory. So Einstein assumed two things to be true in order to develop his special theory of relativity. If these two facts, if either one was proven to be false, then his entire theory would also be false. But that was not the case. So number one, Einstein said that all inertial frames, and if you recall, that means that it's either moving at a constant velocity or it's not moving at all. So all inertial frames means that the frame is not accelerating. So all inertial frames are equally valid. And what this means is that you cannot tell that you're moving within an inertial frame unless you compare your motion to something else. And the reason for that is if your frame is moving at a constant velocity or it's not moving at all the laws of physics still apply. So you can imagine that if you're within your car and it's moving at a constant velocity and you throw a ball up in the air, it's going to go straight up and straight down. So if you're in your car that's moving at a constant velocity and you're within the car, if you threw a ball in the air, it's going to go straight up and straight down because the ball is also moving at a constant velocity. But relative to you, the ball is not moving. If there's an outside observer, so someone's on the outside looking at you throw that ball, what they're going to see is that the ball goes up, but it's also moving at a constant velocity, the same velocity that the car is moving at, and so they're going to see an arc. So if you compare your motion inside the car, if you're moving at a constant velocity, you cannot tell that you're moving. Unless you can look outside and see the trees passing by or the road passing by. But let's assume that there's no windows in this car and it's moving at a constant velocity, you cannot tell you're moving. If someone on the outside looking in can see you throw that ball, they can tell that you're moving relative to them. So that's Einstein's first postulate, that all inertial frames are equally valid. They're all correct. Number two, he argued that the speed of light is constant in all reference frames. So what he said is that in any frame of reference, the speed of light is the same, and the speed is equal to c, or 3 times 10 to the 8 meters per second. So if we have a car, once again, and it has a flashlight at the front, and this flashlight is emitting light particles, these light particles are going to be traveling at speed c. And we're assuming that the car is stationary, so v equals 0. So these light particles are moving at speed c. If the car starts moving, so now it's moving at some velocity that's not equal to 0, and it once again is still emitting light particles, and they're moving at speed c. From the first couple of units, we know that since the light particles relative to the car are moving at speed c, then someone over here should see the light particles relative to them moving at the speed of v plus c. That's what logic tells us. But Einstein argued that no, The person inside the car sees the light moving away from them at speed c, and the person looking at the car approaching them sees the light coming towards them also at speed c. So the speed of light, no matter any reference frame, is always going to be equal to 3 times 10 to the 8 meters per second. So using these two postulates, Einstein derived the theory of special relativity. So one of the consequences of Einstein's theory is the effect of time dilation. And what this means is that time runs differently based on whether you're moving or not. To demonstrate this, we're going to imagine that you have a clock that consists of 2 mirrors. And we're going to emit a light from the bottom clock. It's going to travel up and then be reflected from the top mirror, travel back down. We're going to say a tick on this clock is the time it takes for light to make a round trip up and then back down. And if we assume that this mirror has a length equal to delta d, then we can calculate how long it takes for a tick to occur. It's going to be delta t. The light has to travel up and then back down, so it's traveling 2 delta d, and then it's traveling at the speed of light, so we divide by c. So that's the length of a tick in seconds on this clock. Now we're going to imagine that we have 2 people with this identical clock. Person 1 is going to be stationary, so they're going to have a velocity of 0. They're going to be standing with their clock. When it emits a light, it's going to go up, going to come back down, and they measure their time as delta t equals delta 2 times delta d divided by c. That's how long they measure a tick. We're going to have another person that's moving at some constant velocity. So this person too, and they're moving at some constant velocity. They also have their clock moving along with them. And for them, the light, of course, is also moving at a constant velocity to the right along with them. However, from the moving person's perspective, just like with the ball, the light is not moving relative to them. So when the moving person looks at their clock, the light goes straight up and straight back down. So they also measure their tick as 2 delta d divided by c. Everything is normal. But from person 1's perspective, from the stationary observer's perspective, looking at the moving person, they see their light start at the bottom, but it's moving at a constant velocity with them, so it goes in a diagonal path to the top, and then it comes back down in a diagonal path. So from the perspective of the stationary observer, the light traveled through a diagonal path. Of course, diagonals are much larger than simply going up, and so the stationary observer thinks the moving observer's clock is running slower because their tick is going to take a longer amount of time. Since it's not traveling delta d anymore, it's traveling some other distance. If we look at this distance, so we're going to draw this out. This is the diagonal of the light traveling up and then back down. So we'll say the moving observer has a tick of delta tm, and the stationary observer has a tick of delta ts. So from the perspective of the moving observer, they have a time of delta tm. So within one tick, the train, or whatever they're on, is going to be traveling v delta tm. That's the distance that it travels in one tick. So whatever this is. That means that the base of one of these triangles is half of that, so 1/2 delta, or 1/2 v delta tm. And of course, the height over here, well, the height is simply the length of the clock, so that's going to be delta t. And we'll call the length of this hypotenuse z. If we use Pythagorean's theorem, we can calculate z. I'll use a different color since I've already used green. we can calculate z. So z is going to equal the square root of one of the sides, so delta d squared, plus the bottom side, so v delta t m divided by 2 squared. Obviously, that's greater than delta d, and so the moving person's light did indeed travel a larger distance. And if it traveled a larger distance, so delta tm is traveling to z divided by c. If z is larger, then the length of their tick is going to be longer than the stationary observer. In other words, their time is running slower, and we're going to see how much slower. So if we draw the moving observer's clock from their perspective, their light goes straight up and straight back down. But in reality, it's traveling in a diagonal path since they're moving. And this diagonal path has a distance z. And so the light is really traveling a distance z instead of what they think is a distance delta d. If we calculate what z is in terms of the speed of light, it's equal to the speed of light times the time for one tick, but the light is traveling up and back down, and so we should only consider half a tick. So we'll divide by 2. Now our goal is to be able to compare the moving observer's time to the stationary observer's time. And so we're going to have to use the distance d that the stationary observer is measuring. To do that, we're going to connect back to Pythagorean's theorem, or the result we got from Pythagorean's theorem. So what we'll do is we'll square z first. So z squared is equal to c squared delta t squared divided by 4. This is going to equal the square of what we got from Pythagorean's theorem for z. So z, if you remember, was equal to the square root of d squared plus the velocity of the moving observer times their time divided by 2 squared. Square root all of that. That was z, but now we're looking at z squared, so we'll square all of this. So the square and the square root will cancel out. So we get that c squared delta t squared m divided by 4 is equal to d squared plus v squared delta t squared once again divided by 4. Now we're going to isolate for delta tm and hopefully try to get delta ts on the other side. So if we subtract this guy from both sides and get it to the left side, then we'll factor out the factor of delta t squared m. We get that delta t squared over 4 c squared minus v squared, so this v squared is going to go to the other side, is equal to d squared. Then if we isolate for delta t squared m, we'll see that delta t squared m is equal to 4d squared over c squared minus v squared. Now the key here is that we can remember that the tick for the stationary observer is equal to 2d, not d squared, 2d, or delta d, kind of simplified it here, 2d divided by c. So delta ts squared is equal to 4d over c squared, or 4d squared divided by c squared. We have the 4d squared right over here, so what we have to do is divide the numerator and the denominator by c squared. So delta t squared m is equal to 4d squared over c squared divided by c squared divided by c squared is simply going to be 1 minus v squared over c squared. Now this guy we can replace with delta ts squared. So that's equal to delta ts squared. And now we'll square root both sides. And we find that delta tm is equal to delta ts divided by the square root of 1 minus v squared divided by c squared. And clearly you can see right away that the moving perspector, or the moving observer's time, is not equal to the stationary observer's time as long as the moving observer is moving at some velocity. If they're moving at a velocity of 0, then this whole term is equal to 0, and we get that delta Tm is equal to delta Ts. If they're moving at some velocity that is not equal to 0, then the denominator over here is less than 1, since it's 1 minus some number. It's going to be less than 1, so we're dividing a number by a number that is less than 1, and so we'll get that delta Tm is greater than delta Ts. So time runs slower for a moving observer. Now it's important to note that the moving observer does not notice that their time is running slower. The stationary observer thinks or knows that a moving observer's time is indeed running slower. It's kind of hard to wrap your head around since it's not really logical. You'd think that time is absolute, but right here we've shown that it's relative. And the tick for a moving observer is longer than the tick for a stationary observer. So apart from their times moving at different rates, we can also make a few more conclusions. So we have that the time of the moving observer is equal to the time of the stationary observer divided by the square root of 1 minus v squared divided by c squared. So our first case that we're going to look at is, what if v is equal to c? Then the square root of 1 minus v squared over c squared is equal to the square root of 1 minus c squared over c squared, which is simply 1. So we get the square root of 0, which is 0. Then what we get is that the time of the moving observer is equal to the time of the stationary observer divided by 0, which is equal or approaches infinity, or you could say that it's undefined. What this is saying is that if you're moving at the speed of light, time does not pass. So once you move at the speed of light, time essentially stops. The second conclusion is that let's suppose that the velocity is greater than c. In that case, the square root of 1 minus v squared over c squared. If v is greater than c, then v squared over c squared is greater than 1. 1 minus a number that is bigger than it will give us a negative number. So that's going to be the square root of a negative. And we know that we cannot take the square root of a negative, at least not in a logical way, for it to apply in physics. And so this is straight up undefined. It's not infinity, but it's straight up. We cannot come up with a physically logical number to represent it. And for these two reasons, nothing can move at the speed of light except light, and nothing can move faster than the speed of light. So now we have a question for practice. We have an 8-second interval that's measured on a moving spacecraft. So someone within the spacecraft moving at some constant velocity measures a time interval of 8 seconds. The same interval is measured as 10 seconds from Earth. We want to know how fast the spacecraft is moving relative to the Earth. So the question gives us two reference frames. We have a moving frame, and that's the spacecraft since it's moving relative to the Earth. And we have a stationary frame. Of course, Earth is moving, it orbits the Sun, but Earth relative to itself is stationary. Now in terms of the times, we have to have a time for a stationary observer, or proper time, and a time for a moving observer. Now remember that this 8 seconds is measured inside the moving spacecraft by the person sitting inside the spacecraft. And so for them, they don't know that they're moving, everything seems normal. So that is actually the proper time. That time relative to its observer is not moving. The clock is measured from an observer that's not moving relative to the clock. So our delta TS is equal to 8 seconds. We'll put a star here. The observer of the clock is not moving relative to the clock. So while it's true that the spacecraft is moving, the observer that measured the time that's sitting within the spacecraft is not moving relative to his clock. So that's the proper time. The moving time, or the non-stationary time, is the 10 seconds we got. The people sitting on Earth, they measure the clock as it's moving within the spacecraft. And so that's the moving time. We have delta TS is equal to 8 seconds, delta TM is equal to 10 seconds. You have your Earth, you have your spacecraft. The guys sitting on Earth can see the clock is moving, and so they are measuring the moving time. The person sitting inside the spacecraft does not see that the clock is moving, so they measure the proper time. Now if we plug both of these values into our equation, we have that delta Tm is equal to delta Ts divided by the square root of 1 minus v squared divided by c squared. We want to solve for v, so we're going to isolate. If we multiply the square root, divide by delta Tm, we'll get the square root of 1 minus v squared divided by c squared is equal to delta Ts divided by delta Tm. Then we can square both sides to get rid of the square root. So we get 1 minus v squared over c squared is equal to delta Ts over delta Tm squared. Then we can move the v squared over c squared to one side and bring the times to the other side. So we get v squared over c squared is equal to 1 minus delta Ts over delta Tm all squared. Then we'll multiply by c squared to get c squared, 1 minus delta Ts over delta Tm all squared. And then we can square root to isolate for v. So v is equal to square root of c squared is simply c, and the square root of the rest. Then we'll move to the other side. If we plug in what we have for v, it's equal to c times the square root of 1 minus the proper time is 8 seconds, and the moving time is 10 seconds squared. These seconds will cancel out, and so the only units we have left in the question are the units from c, and c is the speed of light, so it's already in meters per second. So everything works out. We're going to get a final answer that's a speed. So the velocity, or the speed, is equal to 1 minus 8 divided by 10 is the same thing as 4 divided by 5. 4 squared is 16, 5 squared is 25. So that's going to be c times the square root of 1 minus 16 over 25. What's left is going to be 4 plus 5 over 25, so 9 over 25. Square root of 9 over 25 is 3 over 5. And you can leave that as your final answer. So we get that the spacecraft is moving at 3/5 the speed of light. And if you actually plug in the speed of light, you'll get an answer of 1.8 times 10 to the 8 meters per second. So in order for the proper time to be 8 seconds and the moving time to be 10 seconds, then the moving reference frame has to be moving at 1.8 times 10 to the 8 meters per second, or 3/5 the speed of light. Another consequence of Einstein's theory is the myth of simultaneity. So let's suppose that we have our two observers once again. So observer 2 is moving to the right at some constant velocity, and observer 1 is stationary. They're not moving. Now we're going to suppose that we have 2 points that are an equal distance from observer 1. They're an equal distance from observer 1. And we'll say that they're also an equal distance from observer 2, who's moving to the right. And we're going to say that lightning strikes both these points. Of course, lightning is nothing but light, and so it travels in waves. These waves are going to travel to the stationary observer, and since they're going to travel the same distance, the stationary observer sees both strike at the same time. So he's going to deduce that these lightning strikes were simultaneous. They occurred at the same time. The moving observer, the light from the strike in front of him is going to be traveling towards him, and the light from the strike behind him is also going to be traveling towards him. But since he's moving to the right, he's moving closer to the lightning strike to his right and moving away from the lightning strike behind him. So the light from this first lightning strike is going to have to travel a shorter distance since he's moving towards it, and the strike behind him is going to travel a longer distance. So he's going to see the first one happen to his right, followed by the second one to the left. So they're going to say right strike, the right lightning strike before the left. So for the moving observer, they were not simultaneous. And so we can see that the idea of something being simultaneous or simultaneity is time dependent. And we saw that time is relative. It's not absolute. It depends on your reference frame, if you're moving or if you're not moving. So since time is relative and simultaneous events are time dependent, then something that's simultaneous, or an event that's simultaneous in one reference frame, is not necessarily simultaneous in another.